Hi, everybody, and welcome to another thermodynamics module. This is going to be the first module of a number of modules I have planned regarding ideal gases. So we'll talk a little bit about ideal gas equation of state in general, and then do two example problems. All right, I've got to get to my PowerPoint. And here we go, working with ideal gases, and I hope this is going to be, this is demo one of what I hope will be a number of demo videos. And the little icons or little pictures here give you a general idea or a concept of how we're modeling ideal gases. So let's get started. The most basic situation for dealing with ideal gases is for you to learn quickly dealing with the ideal gas equation of state, which is given by this simple but powerful expression, PV equals MRT. And this is for a closed system, because remember, for a closed system, we have a fixed mass. Okay, pressure times volume equals the mass times R. That's going to be a gas constant times T. Now, for either a closed system or open system, do you see we can transform this extensive property into an intensive property by just saying P times little v is equal to RT. So this is going to hold for either closed or open systems. Now, what do these equations mean? What does it mean? It means that the state of an ideal gas, so the state is defined by pressure, specific volume, and temperature. Okay, and it's a relationship of all of those all in one single expression, extraordinarily powerful. And R is called the gas constant, and it's a constant value associated with each particular substance. And I'm going to give you some details on that because a lot of students ask a lot about R. Okay, so what is R? The gas constant for each specific ideal gas is defined by R is equal to R bar divided by molecular weight. And so now you ask, well, what's R bar? Makes sense. Well, R bar is a universal constant. And your textbook does a good job of explaining how all ideal gases behave in very similar ways. And thus, on a mole basis, R bar is universal. And so I do want you to be sure that you can find this little table in your book. This is on that one-page table of conversion factors and constants. And here are numerical values of R bar in both SI and English units. So you definitely need to be able to find these in your textbook. And I suggest you commit both of these to your memory in terms of numerics and units. Okay, so R bar pronounced R bar, universal gas constant. And next question, what's the molecular weight? What's the molecular weight of a substance? It is my hope that you know some of these by heart, either from high school chemistry or your freshman chemistry. Now, if you need a reminder, you need to be able to navigate to this table A1 in your textbook. And here's the molecular weights. Textbook calls it M. I call it MW, molecular weight, of a bunch of substances that are related to our engineering situations. Okay. Be sure you can get to table A1 so you can quickly determine the molecular weight for any substance you might have on a homework problem, quiz, or a test. Okay, and so looking a little closer at molecular weights, what are the units of a molecular weight? In SI, kilograms mass per kilomole. In English, pounds mass per pound mole. Simple as that. And so I'm not going to go any further because I'm going to hope that you master these things in either high school chemistry or college chemistry. I want to suggest that you commit this little list of molecular weights to your own memory. I hope that you know them already. If not, do a little memory refreshing on your own. H2O, water and steam, has a molecular weight of, let's see, 16 plus 2, 18. Air, 28.97. Well, air is a mixture of nitrogen, oxygen, a little argon, a little CO2, and ultimately you do the math and you get a molecular weight of 28.97. And then if all of these other ideal gases follow, and hopefully you've got these in your memory, or we'll do a little work to memorize these. In engineering practice, it's perfectly acceptable to use these integer values for the molecular weights of these substances, except for air. Now, it's very common and reasonable that a student will say, I'm reading a problem and all I see is a word. I don't see in the problem, use an ideal gas or use a phase change substance. How do you determine what to use? Do I use an ideal gas model, or do I need to use property tables for phase change substances? Well, here's a little guidance. You have to use Common Sense 101. That's what I call it. And so you can see this list that I've listed here on the slide are commonly recognized as gases, right? There are exceptions, aren't there? For example, CO2. If it's very, very cold, it becomes dry ice. Well, that would be a phase change substance. But in general, in most cases, you're going to recognize these as ideal gases and model them as such. Air. I would say in this class, when you see the word air, that's an ideal gas. Now, phase change substances, you look for words. When you see the word water or the word steam, that's H2O. That's a phase change substance. Also, you see the words refrigerant R22, R134A, propane, and also even ammonia when it's used as a refrigerant. In very large industrial refrigeration systems, we use ammonia as the refrigerant. So those you recognize as phase change substances. You're going to go to the back of your book to your property tables to get properties there. Okay, we're blazing along. Let's look at example 1. This is a very basic problem, and I cover it because you really need to master this and quickly. Air is contained within a piston and cylinder with a volume of 0.5 cubic meters, a temperature of 25 degrees C, and a pressure of 100 kPa. Very representative of something you would see a tank at atmospheric conditions. Determine the mass of the air in this cylinder, the specific volume, and the density. Sounds pretty easy. And I'm hoping you're saying, oh man, I'd have this nailed. Okay, let's go through some of the details. And here's the solution approach before we crunch numbers, and we will crunch numbers. I'm going to write down the word air, model as an ideal gas. The next thing I write down is the ideal gas equation of state for a closed system, PV equals MRT. You got to memorize that. I'll solve for M. M is PV over RT. Oh, I need to get R for air. I'm going to use R bar over the molecular weight. I'm going to watch out for my units, and we're going to do a units check and do the math. Then specific volume is simply the volume that we're given divided by the mass we found, and rho, the density, it's the reciprocal of specific volume or mass over volume, whichever you prefer. Those are identical. Look, you're going to be doing this approach hundreds of times throughout the rest of this class, and that's why I'd like you to spend a little time working to master this example problem. Okay, and so here's the numerics. I solved this in Excel, and here's a screenshot of it. Let's do a little units check first. M is PV over RT. Recall that a kilojoule is a kilonewton meter. A kilonewton meter. A joule is a newton meter. Okay, units checked. So pressure, kilonewtons per square meter. Okay, that's kPa times V, volume, cubic meters, divided by kilojoules per kilogram degree K for R. R for air is going to have units kilojoules per kilogram degree K. And so you see that I sneaked in a kilonewton meter, same thing, times temperature, which must be in absolute temperature degrees K. So we'll strike out everything, and then we'll observe. We've got our newtons struck out, our kilos struck out. So we've got kilograms. So we're going to be good learning from this units check. Got to have temperature in degrees K, not degrees C. Must have pressure in kPa, kPa, to get all of our units to cancel. So here's the numerics. Defined R, molecular weight, 28.97. R bar, went to the book, write down 8.314 kilojoules per kilomole degree K. R for air, 0.287. You might want to memorize that because we have so many air problems in this course. T, 25 degrees C, I've got to add 273 to that. Just add the integer, 273 to it. Okay. Volume given, pressure given in kPa, all right? So now we're solved straight out. M is PV over RT, plug and chug. M is 0.5846. Okay, specific, now we're home free. Specific volume, V over M, 0.8552 cubic meters per kilogram. And rho density is the reciprocal of specific volume, 1.1693 kilograms per cubic meter. Easy as can be, but master this. Let's recap. And so what I did was write out our results in sentences. Mass of the air in the cylinder is 0.585 kilograms, period. The specific volume of the air is 0.833 cubic meters per kilogram. The density of the air is 1.169 kilograms per cubic meter. Notice how I just expressed 3 to 4 significant figures in the answers that I wrote out. Writing out 8 significant figures, that's too many. That's not good engineering practice. Okay, and my little yellow note here, this is as basic as it gets. You've got to master this process so that you can analyze more complex thermal engineering situations. We're blazing on to example 2, refrigerator. The air enclosed inside a refrigerator. Air is contained within a closed refrigerator with a volume of 15 cubic feet. That's about typical. A temperature of 38 degrees F, that's pretty typical. And a pressure inside the refrigerator of 14.7 PSIA, pounds per square inch absolute pressure. Problem is, determine the mass of the air contained in the refrigerator, the specific volume of the air, and the density of the air. Solution approach. Wow, I copied and pasted my slide. This is exactly the same word approach as the SI. Exact same approach as example 1. Go to our one-page conversion factor and constants table and fish out R bar in English is 1545 foot-pounds force per pound mole degree R. It is worth memorizing this. Okay. The molecular weight of air, 28.97 pounds mass per pound mole. It is worth memorizing that. And so R for air, we're going to do the math. R bar of the molecular weight. R for air, 53.33 foot-pounds force per pound mass degree R. So you're going to be doing this hundreds of times in this class, so you might as well memorize R for air as well. All right, let's go through the solution. Let's check units first. And I've got a hint. So instead of going through and seeing we've got a blunder, I've got the hint is get pressure into units of pounds force per square foot first. That's my hint, just for a little time savings. So we're going to check our ideal gas equation of state. M is PV over RT. All right, pressure, pounds force per square foot. Volume, cubic feet. R, foot-pounds force per pound mass degree R. Temperature, absolute temperature must be in degrees R. Okay, so actually this was a little easier to visualize. Once we took that hint and transformed our pressure into pounds force per square foot, this becomes easy to cancel, and we see that our mass is in pounds mass. Okay, let's go through the numerics. Molecular weight, 28.97. R bar, 1545. Foot-pounds force per pound mass degree foot-pounds force per pound mole degree R to give R for air is R bar over the molecular weight, 53.33 foot-pounds force per pound mass degree R. Temperature is 38 degrees F. Add the integer 460 to it to get 498. Volume is given. Pressure in pounds per square inch. Look at this. Conversion. I put in 144 and wrote out the conversion. 1 foot squared equals 12 times 12 inches squared. Okay, remember my little units module we talked about and multiplying things by unity. So visually, you can see how to turn that into unity, multiply unity by the pressure to get the pressure in pounds force per square inch. Got a little typo there. It's not PSIA. Okay, check that typo. We need to check that. That's going to be pounds per square foot. That's a little blunder there. Okay, that's pressure in pounds per square foot. Okay, so the mass then is PV over RT of 1.1955. Okay, make a little note. This pressure. I think with your eyes you can see my blunder, correct? Okay. The mass, 1.196 pounds mass. Now, it's easy sailing here. The specific volume, let's just remember the definition of specific volume. The volume divided by the mass, or 12.55 cubic feet per pound mass. Density, rho. Rho is P over RT, or 1 over the specific volume, 0.0797. Okay, so sorry about my typo blunder. It's a good example of a copy and paste blunder that I didn't pick up. And key learnings: you've got to have temperature in absolute temperature degrees R. You've got to have pressure in pounds force per square foot. Okay, the recap of example 2. The mass of the air in the refrigerator is 1.19 pounds. Just gave 3 significant figures. The specific volume of the air is 12.55 cubic feet per pound. Gave 4 significant figures there. Density of the air, 0.0797 pounds per cubic foot. I expressed that to 3 significant figures. So let's recap this module as a whole. The ideal gas equation of state is a powerful problem-solving tool for you as an engineer. It only applies to ideal gases. A lot of folks, a lot of students, once you have this equation of state, they want to apply this handy relationship to everything in the world. Don't do that. This only applies to ideal gases. Okay. The power of it is that it relates 3 intensive properties: pressure, specific volume, and temperature in a single expression. Very powerful. So 3 intensive properties all related to each other in one equation. And so a key to success in doing the 2 example problems is checking your units, getting your units straight. Okay, and then the other key takeaway is this is as basic as it gets for ideal gases. So you're praying for ideal gases on problems, okay, because it's pretty basic, but you've got to master this starting point to proceed ahead. Now, in the next module, what I'm hoping for is to talk about processes going from state 1 to state 2 for ideal gases, and how the ideal gas equation of state can really be a powerful problem solver for you. Okay, that gets us out of the PowerPoint, and I hope you've picked up some good tricks of the trade, and hope you're inspired to try to memorize maybe some things that you haven't memorized yet, because it will help you in the speed with which you can do your homework problems, your quiz problems, and your test problems. Okay, talk to you again soon.